You ever look at a chemical drawing and just get the feeling that it's, well, not telling you the whole story? If you have, you're definitely not alone. Today, we are diving deep into resonance, one of the most important ideas in chemistry. It's the key to understanding why some molecules are incredibly stable and how their electrons can act like they're in multiple places at once. So let's decode this blueprint.
All right, here's our game plan. We're going to start with a really cool molecular mystery that had chemists scratching their heads for a while. Then we'll see how resonance comes in and just solves it. After that, we'll dig into why this whole process creates so much stability, learn the rules of the road for drawing electron flow, figure out how to rank different structures, and finally, see it all in action with what we call electron pushers and pullers.
So, our story begins with a genuine puzzle, a molecule that just seemed to laugh in the face of the simple drawing rules that worked for everything else. And here it is. Meet benzene. Now, if you draw it using the standard rules, you get alternating single and double bonds. Simple enough, right? Well, that drawing predicts two different bond lengths, a longer single bond around 154 picometers and a shorter double bond at 134. But here's the kicker. When scientists actually measured it, that's not what they found. Not even close. All 6 bonds were perfectly identically the same, 139 picometers long, right in between the two. So what gives? Our drawing is wrong. The answer, it turns out, isn't to just pick one drawing. The real solution is to understand that the true nature of the molecule is something in between our drawings. And this, right here, is the core idea of resonance. So on the left, you see our 2 possible attempts at drawing benzene. We call these canonical structures. Now, this is absolutely crucial. The molecule is not flipping back and forth between these 2 drawings. That is not happening. These are just our limited human tools for trying to represent it on paper. The actual physical reality is what you see on the right, the resonance hybrid. It's one single, blended, incredibly stable state that's an average of our drawings. So let's just lock in those definitions right now. Canonical structures, they're hypothetical. Think of them as thought experiments that don't actually exist. The resonance hybrid, that's the real deal. That's the molecule as it sits in a beaker. I love this analogy. A rhino isn't a unicorn and a triceratops switching back and forth really fast, right? It's just a rhino. The hybrid is the rhino. And this image shows that reality beautifully. You've got this fixed framework of carbon and hydrogen atoms. They're locked in place. But the pi electrons, the ones from the double bonds, they aren't stuck between any 2 atoms. Instead, they're delocalized, which is just a fancy way of saying they are smeared out over the entire ring. It's like a donut-shaped cloud of electron density, shared equally by all 6 carbons. So we get what resonance is. But the next big question is, why? Why does this happen? Well, like so many things in science, the answer comes down to energy and finding the most stable place to be. This energy diagram tells the whole story. See how high up those hypothetical canonical structures are? They're high energy, kind of unstable. But the actual molecule, the resonance hybrid, is way down at the bottom of that deep energy valley. By spreading out its electron density, the molecule dramatically lowers its overall energy. And that difference, that energy drop, has a name: resonance stabilization energy. It's the whole payoff. The more you can delocalize, the more stable you become. Now, to really work with resonance, we need a consistent way to show how we get from one of our hypothetical drawings to the next. We basically need to learn the language of electron movement. And our main tool, our pen, is the curved arrow. This is the official grammar of resonance, and it is super precise. The tail of the arrow always starts at a source of electrons, either a lone pair sitting on an atom or the electrons in a pi bond. And the head of the arrow points to the exact spot those electrons are moving to. No exceptions. And with that arrow come 2 non-negotiable golden rules. First, atoms never ever move. The skeleton of the molecule is fixed. Only electrons get to travel. And second, you can't create or destroy electrons. The total count in the molecule has to stay the same from one drawing to the next. You're just reorganizing them. Okay, remember how we said the hybrid is a weighted average? Well, that implies that some of our drawings, some of those canonical structures, are more important. They contribute more to the final real picture than others. So how do we figure out which structures are the heavy hitters? It's actually pretty straightforward. We've got this handy checklist. The best, most stable structures, the ones that are the biggest contributors, will have the most covalent bonds possible. They'll have complete octets of electrons around as many atoms as possible. They'll have minimal or zero charge separation. And if there is a negative charge, it had better be on the most electronegative atom. Let's use this checklist on a real example. So structure I, it's the star of the show. Maximum bonds, all the octets are complete, no charges anywhere. This one is by far the biggest contributor to the hybrid. Structure 2 is okay. It has charge separation, which isn't great, but at least the negative charge is on the oxygen, which is the most electronegative atom. So that makes sense. But structure 3, oh boy, that one's got a positive charge on the oxygen. That's a huge red flag. This structure is so unstable, it contributes almost nothing to the real picture. Okay, so we've got a handle on how resonance works within a core molecule, but things get really interesting when we start attaching other chemical groups to that molecule. For resonance to really spread its wings, you need what's called a conjugated system. The best way to think about this is as a molecular highway. It's a continuous, unbroken path of alternating single and double bonds that allows those delocalized electrons to cruise from one end of the molecule to the other. Now, when you attach a new group to this highway, it's going to do one of two things. It'll either donate electrons, pushing them into the highway, we call that a positive R effect, or it'll be electron withdrawing, pulling electron density out of the highway, and that's a negative R effect. It sets up this incredible electronic tug-of-war. And here are two perfect examples. On the left, you've got an amine group. That nitrogen has a lone pair of electrons it's more than happy to share, so it pushes electron density into the ring. It's a classic plus R pusher. On the right, you've got a nitro group. It's full of electronegative atoms, and it powerfully pulls electron density out of the ring towards itself. It's a strong minus R puller. And these effects completely change the reactivity of the molecule. So let's tie this all together with one big unifying analogy. Think of it like an electrical circuit. The conjugated system, that highway of bonds, is the copper wire. The delocalized cloud of pi electrons is the current flowing through that wire. And that attached group, the pusher or the puller, that's the battery, the power source that's driving the current one way or the other. So, the most important thing to take away is that resonance isn't just a quirky drawing convention. It is a fundamental physical principle that gives molecules incredible stability and directs how they behave. It's why dyes are colored. It's part of how our DNA resists damage. It's just everywhere, which really makes you wonder, doesn't it? Where else in nature or in technology is this principle of delocalization, of spreading the load to create a stronger, more stable system at play?